Hi, my name is Phil Smith and I've been working with Bill Vogel. We are both graduate students at Syracuse University enrolled in the Enterprise Wireless course this spring. We conducted a general evaluation of the Microsoft Wireless Display Adapter, which is a mouthful, so I'll be referring to it as the MWDA. We think the MWDA may be a better solution in the enterprise for screen sharing compared to consumer devices such as Apple TV and Chromecast, both of which get cast from source devices through an already established Wi-Fi AP. 802.1x's use on the enterprise network typically isn't supported on these consumer devices. If a casting device is able to connect, it relies on discovery processes between the casting and source device on the network that might be in a separate subnet, which discovery can't currently work around. MWDA uses technologies that establish direct connections between source and casting devices, negating the requirement for an established network as shown in this drawing, the source being the laptop and the MWDA depicted by the TV. The supporting technologies for MWDA are WiDi, which is a proprietary Intel technology, and Miracast, which is a Wi-Fi Alliance open standard. WiDi supports Miracast, so effectively it is a superset of it. Miracast is layered upon many different technologies, including Wi-Fi Direct, allowing direct connections between devices. You can learn more about Miracast and find certified devices on the Wi-Fi Alliance's website shown below. The MWDA device is a HDMI dongle with a USB tail for power. It currently costs about $60 and is compatible with Windows 8.1 and higher devices and Android 4.2.1 and higher devices. It is a wireless HDMI cable alternative, meaning it mirrors or extends an entire display just like an HDMI cable. It does not support streaming from independent apps like other solutions mentioned here. For our test, we examine one of two different connection states from a source device perspective. We do not examine the ad hoc pure state in which the only connection being made is from the source device to the MWDA with no infrastructure Wi-Fi connection at the source device. In this environment, all digital material has to be stored on the source device as it would not be able to access any outside services. In the second state, which we have called hybrid mode, a source device is connected to a Wi-Fi AP to gain network and/or internet access as in normal operation. A separate connection and network is then established to communicate with the MWDA. The catch is that most source devices will only have a single Wi-Fi chipset, allowing it only to communicate on one channel at a time. If the source device with a single Wi-Fi chipset is first connected to an AP, in this example the intranet network, the same channel must be used to connect with the MWDA, in this case channel 11. First, in Windows, a virtual NIC is created, as shown here. The source and MWDA negotiate a new SSID to be used exclusively between the virtual NIC and the MWDA, in this case the direct preface network. Essentially, the physical NIC splits the time it spends on each network depending on the ad hoc network load. A virtual NIC is still created in the ad hoc pure mode for the possibility of Wi-Fi network connection. During our ad hoc pure connections, the MWDA connected to channel 11 and 149 depending on what band we were using. This may differ in other locations as we believe it was the result from the Wi-Fi environment present. We wanted to know how Wi-Fi data throughput was affected while simultaneously connecting to an MWDA. How will maintaining a Wi-Fi direct connection affect the throughput between a source device and a Wi-Fi AP? In our test, we used the MWDA device, a Nexus 5 for Android, a Surface Pro with Windows 8.1, an HP DV6 with Windows 8.1, and a Netgear R6300 router along with a Windows 8.1 iPerf server wired directly to the gigabit port on the back of the router. This is the iPerf client string we used for all source devices tested. We established a baseline of Wi-Fi speeds from source devices to our server without connecting to the MWDA. In Phase 2, we kept our Wi-Fi connection and also connected to the MWDA to set up the hybrid environment. We then ran the same speed test from our source devices to the server. In Phase 3, we disconnected from the MWDA and retested our Wi-Fi connections from our source devices to the server. This produced some unexpected results, which led to Phase 4. We then reset our source's Wi-Fi connections and retested. Interestingly, in most cases, the disconnect numbers don't return to baseline numbers as expected. We weren't able to get the speeds back up until the Wi-Fi was reset. We investigated the odd disconnect speeds by looking at what was going on in Wireshark from the Surface Pro. We found out that our ad hoc group membership wasn't really completely terminated until the next device tried connecting to the MWDA. The Nexus 5 had the largest gap compared to the other 5 gig device. Our theory is that the Nexus has fewer antennas, therefore has a harder time dividing bandwidth, whereas the Surface Pro is more or less a desktop device built for performance that has multiple antennas, resulting in a flatter pattern. While digging around on Wireshark, we found some other things, such as passwords being sent in the clear HTTP text, which also led to us finding a way into a web interface on the device, as shown here, which we'll post a how-to shortly after posting this project. But it was a learning experience, and we really appreciate you listening and watching. Thanks.